Any queries? Okay. Now, in the previous class, we have used Reynolds transport theorem in a translating frame, and I've given you the motivation for the mathematical expressions that we were using. Now, I'll give you an alternative derivation today using the Galilean transformation, which is a little more direct method. Okay. So recall this Galilean transformation from the stationary frame on the left to the moving frame on the right. Okay. So the coordinates of a point P, you can refer to this coordinate system x prime, y prime, z prime, or
Sir,
to the,
have you shared the screen?
yeah. You have a query?
Sir, the screen isn't visible.
You are unable to hear me?
No, the screen isn't visible.
Screen is not visible.
Yes, sir.
Oh, okay. Sorry. Thank you. I forgot to share. Okay. So recall the Galilean transformation. We had a fixed coordinate system shown in black here, O, X, Y, Z, and a translating coordinate system, O prime, X prime, Y prime, Z prime, in red here. Now, coordinates of a point P may be described by the triplet X, Y, Z or the triplet X prime, Y prime, Z prime. And these, as we have seen before, are related in this way. So we have chosen a coordinate system where the Y and Z coordinates are the same in both the systems, and the X coordinate differs by the distance between the axis OY and the axis O prime, Y prime. And there's an initial distance at time t equal to 0, which we called x subscript in it. And the distance keeps on increasing with time by this constant u multiplied by t. Okay, so we are looking at a case where u is constant. Now, we have gone through this before, but I want to.
Sir, the screen still isn't visible.
Yeah, pardon?
The screen is still isn't visible.
Screen is still not visible.
Now it's visible, sir. I don't know.
Yes,
Okay.
sir, it is visible.
Okay. So this document I uploaded last week. So you may have already downloaded and seen it. Okay. But there's one aspect which I have not discussed in the class, so I'm doing it today. Okay. So using this Galilean transformation, you can start with a mathematical expression for Reynolds transport theorem in a station with reference to this coordinate system on the left, and get an equivalent mathematical expression using derivatives with respect to this coordinate system on the right. So we have gone through this before. This is the forward transformation, and where you have the prime quantities on the left and the original quantities on the right. And this is the inverse transformation, where the prime quantities on the right and the original quantities on the left. Now, the position vectors you can write as using x, y, z and the unit vectors ex, ey, z, or using x prime, y prime, z prime and the unit vectors. Now, since the axes are parallel, the unit vectors are equal. They all have magnitude 1 and they point in the same direction. So parallel vectors, are equal if the magnitude is the same. Now, if you use the chain rule and look at the forward transformation, starting with x, y, z, t, so any quantity is a function of 4 arguments, x, y, z, t, any flow variable. The same flow variable you can write as a function of x prime, y prime, z prime, and t prime. Although t prime and t are the same, I've introduced the symbol so that you don't make a mistake while applying the chain rule. So you have two alternative spatial descriptions. You can say any flow variables phi, which can be Vx, Vy, Vz, or the pressure P, can be expressed as a function f1 of x, y, z, t, or another f2 of x prime, y prime, z prime, t prime. And while you can find the relation between the functions simply by substituting this transformation here, it's easier to use the chain rule to find a relation between the derivatives. So you can find very easily that the spatial gradients are the same. So the gradient operator and divergence operator are the same, but there's a difference in the temporal derivative. Okay. So the temporal derivative in the stationary frame is the temporal derivative in the moving frame minus u times a convection term is coming in, del phi del x. Okay. You can write it as del phi del x prime. This comes naturally when you use the chain rule, but del phi del x prime is the same as del phi del x. So I can write the, if I transpose this to the other side, I have a similar expression where on the left-hand side I have the temporal derivative in the translating frame, and right-hand side you have the temporal derivative in the stationary frame and an additional term. Okay. And we argued that the two, so flow is steady in the stationary frame if del del t is 0. Flow is steady in the moving frame if del del t prime is 0. Okay. And I've given you this example before, that when an airplane is moving, the flow induced by the plane, the fluid here ahead of the nose of this airplane will be pushed. Okay, this is an unsteady flow as measured by observer A. But if you have an observer sitting on the plane, okay, you will see a steady flow with the plane, the velocity of the plane is 0, but the fluid is moving in the opposite direction. So you can take a Galilean transformation and relate the two derivatives. Okay. So here del del t prime will be 0, but del del t will be non-zero. And the application of this to the Pelton turbine, we have seen before. The bucket or blade is moving. So the streamline pattern, the relative streamline pattern is moving with reference to this frame. So flow is unsteady. But if you have a reference frame attached to the translating vane, an observer sitting in that vane will see a stationary streamline pattern. However, you see this central streamline, relative streamline, which will come and hit the bucket at this point. So this will be a relative stagnation point. So the pressure here will be higher than the pressure at point 2, 3, and 4. And the velocities here is 0, relative velocity here is 0, and relative velocity here is Vj minus u. So you see that with respect to x, there is a change in the velocity and the change in the pressure. Now what will happen is, that means del phi del x is non-zero, or equivalently del phi del x prime is non-zero, which means that the difference between the two temporal derivatives is non-zero. So both cannot be 0. Okay, so we cannot have a flow which is steady in both the moving frame and the stationary frame unless you say that u is 0. But if u is 0, there is only one frame, which is the moving. Both are stationary frames. Okay. There could be two frames, sorry, but both are stationary. Now, what you can do is use the relation between the temporal derivatives to get an expression for Reynolds transport theorem. Let me see, I'm unable to find it here. Okay, then it might be in another document, sorry. So let me close this and open another document. Okay, sorry about the interruption. All right, now, so in Reynolds transport theorem, you have a term, unsteady term del del T of rho phi dV. Now, del del T I can write as del del T prime minus U del del X. Okay, so this volume integral then I can write as the sum of these two volume integrals. One involving del del T prime, other is minus U del del X. Okay. Now U is a constant, but the speed of the translating frame is constant. The capital U inside and write U del del X of rho phi as del del X of rho phi U. Now, if I consider a vector, so this is a product of rho, phi, and u, three quantities. Now consider a vector with magnitude rho, phi, u, and direction ex. Okay. If you take the divergence of this, it will have only the x derivative because the y and z components of the vector are 0. Okay. So del del x of a quantity I can write as divergence of that quantity multiplied by ex. So this is del f del x, that is divergence of f times ex. Now u times ex I can write as the vector u, the velocity. U is the speed and v, this boldface u is the velocity of the translating frame. And once you write this quantity here, the function that you're integrating on the second term in this equation as a divergence, you can use the Gauss divergence theorem and convert it to a surface integral. Okay. So divergence of rho phi u then will be rho phi u scalar product with the unit vector, unit outward normal to points on the boundary, control surface. So these are the unit vectors at different points on the control surface bounding the control volume. So therefore, the integral of del del t, the volume integral of del del t here I can write as the volume integral of del del t prime minus this surface integral. Okay. And in Reynolds transport theorem, we have two terms. One is this unsteady term, other is the flux of the property converted by the absolute velocity. So there are two terms here on the left hand side which you see in any book on fluid mechanics when you look at Reynolds transport theorem. So the first quantity I can write as the difference of these two integrals. Okay, so then I can look at this. See here the second integral is rho phi multiplied by v dot n, and this is minus rho phi multiplied by u dot n. So I can club it together and write it as volume integral of del del t prime, and surface integral is now v minus u. Okay, so this quantity, the absolute velocity or the velocity of the fluid in the stationary frame minus the velocity of translation of the moving frame will give you the what we were calling w or v prime, the velocity of the fluid as seen by an observer in the moving frame. Okay, so this is an alternative derivation if you had some problems or did not like the approach which I used in the previous class. This is another way of convincing you that the sum of this two is the sum of these two. Okay, so on the left hand side here you have the temporal derivative in the stationary frame, and the convective velocity is the fluid velocity measured in that stationary frame. And here on the right hand side you have the temporal derivative in the translating frame, and you have v minus u, the velocity as measured in the translating frame, the fluid velocity as measured in the translating frame. Okay. So this I'll check whether the uploaded version in Teams is this version, or if I've added it later, then I'll remove that file and change it to this one. Okay. All right. Now let me close this file and open another one. Okay, so let us come back to the Penton wheel. Now this document is becoming very large. So what I'll do is subsequent material that I'll add, I'll prepare a second file on the Penton wheel. This is the size of this file is becoming large because there are many images. Okay, so we were looking at prediction using the balance of linear momentum. So last time we considered a control volume, which I've shown over here. We took a control volume which included the solid section of this vein. Okay. Now you might have an objection because when we derive Reynolds transport theorem, we consider only the fluid region. And here we have taken a control volume which includes the solid as well. And this is what you find in almost all undergraduate books that are available to you. Okay. Now can it be done by taking control volume which does not include the solid vein? And the answer is of course yes. As you might have noticed, when you solve problems in mechanics, sometimes the same problem can be analyzed using two different free body diagrams, and you'll come up with the proper answer. Okay, so here also today I'll show you that we need not have a control volume which cuts through the solid surface. But I told you why we have done it, because then the net force due to pressure becomes zero, with the assumption that the pressure in the liquid at section 2, at section 1 and section 3 is atmospheric pressure. The justification for that is that the jet is surrounded by air on all sides, and the streamlines at these sections are almost straight lines with negligible curvature. So the centrifugal effect can be neglected. Okay. Now today what I'll do is I'll do it in another way. So let us look at an alternative, more direct method of estimating the force on the blade. Now notice that I am not saying calculating the force, I am deliberately using the term estimating because we are making many approximations. Engineering is full of approximations, and in particular fluid mechanics is full of approximations. So you want to get an estimate which may not be the right value, exact value, but an engineer doesn't always need the right value. He may be happy with the prediction which is close. All right. Now let us look at the net force on the blade, which is translating at constant velocity. Well, if the blade is translating at constant velocity, then the acceleration of the blade is zero. So the sum of the forces will be zero. So here I have not shown the body force. I've just shown the free body diagram with the vein and the distributed force due to pressure outside. So you have air on the right hand side. So the value of the pressure is PA. You have air on the left hand side here. So the value of, sorry, you don't have air on the left hand side. You have liquid. So this is the wetted surface of the vein. So the pressure here is more than atmospheric pressure. The reason being that when the flow is deflected, the streamlines move in a curved path. So while at the free surface of the jet, pressure is atmospheric pressure, if you move from the free surface radially inwards, outwards, towards the inner surface of the bucket or the wetted surface of the bucket, the pressure will increase. So at this point here, we are saying pressure is atmospheric pressure. At this point, it is atmospheric pressure. But at points inside, the pressure will be more than. So the gauge pressure here is going to be 0 on the right hand side, 0 at section 3 and section 2, but non-zero here, positive over here. And this is the stagnation point. And the pressure at the stagnation point will be PA plus half rho Vj minus U whole square. Now, why is it not half rho Vj squared? Because the flow is unsteady in the stationary frame. So we cannot apply Bernoulli's equation using the velocities in the stationary frame. But as we have seen, the flow is steady in the translating frame, and Euler's equations of motion are invariant. So they have the same form under the Galilean transformation. So we have a Bernoulli equation in the translating frame. So if the flow is steady in the translating frame, you can apply Bernoulli's equation. The difference is that you have to use the relative velocity. Okay. So if you go back and look at this point here, when the jet is coming out, the absolute velocity is Vj, as seen by an observer in the green frame on the left. If you have an observer sitting here in the moving frame, the fluid velocity relative to him will be Vj minus U, which is capital U, which is the speed of the bucket. So using that, so you will have a streamline, the central streamline, which will move this way, and the relative velocity at this point O prime will be 0. And at the relative velocity just at the exit of the nozzle will be Vj minus U. So the pressure plus kinetic energy, relative kinetic energy at this point will be the pressure plus the relative kinetic energy at this point. And the relative kinetic energy here is 0 because streamlines will be intersecting. So when two streamlines intersect, in this case of course relative streamlines, the relative velocity there has to be 0. So you can see rather easily that the pressure at this point on the splitter of the ridge, okay, is more than the atmospheric pressure by this amount, half rho times Vj minus U whole square. So this is the maximum pressure, and pressure at other points will be less. Now, if you look at the net force due to pressure on just the bucket, not the bucket plus the liquid jet, all right, then you see there is a non-zero force which will act to the right. So there must be an external resisting force to prevent it from accelerating, and that I've shown over here. Okay. So you will have, if I call the external force the vector F with the subscript B for blade, and the net force due to pressure is minus integral of P and dA over the surface of the blade plus the weight of the blade. This must add up to 0. So the force on the blade is simply the force due to pressure minus the weight. But this is a integral over a region which is not your control volume, just the bucket or vane. Okay, surface of the vane, but still it's a closed surface. So I can replace P by P gauge. This we have shown before. So it's easier to work in terms of P gauge. The reason being P gauge is 0 on most parts of the surface. So I've shown another figure here. You have air on the left. So on the surfaces which I have marked in red, these are exposed to the atmosphere. The gauge pressure is 0. And this blue surface here is what I'm calling the wetted surface of the vane or blade, which is adjacent to the impinging liquid. Here on this surface, the gauge pressure is more than 0. It's 0 at this point, this tip, and this tip over here. Okay, it's going to be maximum at the center point over here. Now, we'll use a control volume now, which will not cut through the solid surface. So this is a second approach, a second control volume. So we have one phase of the control volume which is coincident with the inner surface of the vane, not the outer surface. So this is a wetted surface, and this I'm calling 4. So this inlet I'm calling section 1. This outlet I'm calling section 2. The second outlet I'm calling section 3. And this wetted surface of the vane I'm calling surface 4. And the remainder you can say is R minus R1 minus R2 minus R3 minus R4. So if I take a point on this surface, the wetted surface, the unit outward normal here on section surface 4 I'll call n with the subscript 4. The hat and top or the caret sign indicates the magnitude is 1. So when I'm writing by hand, I'm using this hat sign or caret sign to indicate unit vectors. But when I'm typing it in, I'm just using boldface. So you see that the integral over the surface integral, I can split into a surface integral over the wetted surface. That means this blue surface. Okay. And an integral over the non-wetted surface, which is del R blade minus del R wetted. So this second integral is over the red surface. And on the red surface, the pressure, gauge pressure is 0. Okay, so this integral will not contribute force, the external force. And instead of n here, I can write minus n4. Why minus n4? Because this is when I'm looking at the pressure force on the vane surface, I have the normal pointing outwards. Okay, and I'm going to use the control volume to estimate that integral, where I have n pointing towards the vane. Okay, so if this is plus n4, then this vector will be minus n4. Okay, so you have instead of plus n minus n4 here, and this will be 0. And this part I've kept as it is. Now this whole thing I've rewritten in this way by removing the middle term here. So if the function you're integrating is 0, this is like a definite integral over a region, so the value will be 0. Now, G does not have an x component. Okay. So we are interested in the force, horizontal force. Okay. X direction is horizontal. So if I want FB, the vector, it is minus FB Ex prime. Why? Because I chose my direction in this figure, free body diagram, this way. Okay. Because intuitively I expect that if I take the direction from right to left, the value will be positive. Because the pressure on the left is more than the pressure on the right. And the sum of the forces is 0. So you have the first quantity then is minus Fp times the unit vector pointing to the right minus the weight of the blade. And if I look at only the x component of this vector equation, okay, then Gx is 0, so this is not there. Okay, so on the left hand side of this equation, if I write minus Fb times Ex, the second term will not contribute to the x direction force, and from this one you get minus n4x. So you have minus on the left hand side and minus on the right hand side. So the minus n cancels out, and the magnitude of the force, which I'm calling F subscript B, B for blade. Okay, and this force is as the direction is as assumed in this figure, from right to left, and the vane is moving to the right. So this will be the gauge pressure over just the weighted surface, the blue surface, into the x component of the vector, which we are calling n4. Okay, so this del R with the subscript wetted, okay, is actually what you may call del R4. That is the surface which I am calling 4 in this figure below. Okay. Now, so one way to evaluate the force on the blade is to find out the gauge pressure distribution on the inner surface of the blade and multiply it by the x component of the outward normal here, normal pointing outward to the control volume, and evaluate this integral. You may, as an engineer, use a numerical method to evaluate the integral. Okay, if you wish, but then you need to either measure the pressure distribution on the surface or be able to calculate the gauge pressure as a function of x, y, z. So you need, if you move along the wetted surface of the blade, you need to know how the pressure varies along the blade. One way to do it is to solve the non-Euler equations, but those are nonlinear, coupled equations. and not ordinary differential equations. These are partial differential equations. So that is not easy to do. And if you want to include the viscous effects, then you might as well solve the Navier-Stokes equations. But that will require use of techniques of CFD, or computational fluid dynamics. In this course, we want to come up with a simple estimate. So what we'll show is that although even when the spatial distribution of the gauge pressure is not known, the value of this integral may be estimated using a global balance of momentum. So this philosophy I want to instill into you, that you can get exact results by solving the governing partial differential equations by a numerical method. Okay, and today there are many programs available. You may get the source code also, or you can use commercial software. Maybe you'll not be able to see the source code, but if you shell out money, you can buy the software and learn how to use it. So you have to prepare an input file, and then you'll run the program and you'll get an output file. Okay. But as an engineer, you may sometimes be happy with the estimate which is not that exact, not that accurate. And that you can get by using a global approach. So we have been using so far the Reynolds transfer theorem. You can do that also. You can apply Reynolds transfer theorem to this control volume shown in this figure, which does not include the solid surface. Okay. But there's another way to do it, is you can integrate the differential equation representing local balance of momentum. And this I'll show you will give you the same result. Okay. Now if you look at the local balance of x prime momentum, this we have derived using the Galilean transformation. This is the Euler's equation in the translating frame. So I've used del t prime here, divergence grad prime here. This is the x component of the velocity, and this is the vector v, the relative velocity. And this is gx prime and del v del x prime. So this is valid at each and every point inside this control volume, just the liquid region. So this is just the liquid density here. Okay. And this, as I've told you before, is what you may call the conservative form of the equation. So this term is actually, you can write it as rho del t of w plus w dot grad rho wx. Okay, but we'll be using the we'll integrate this equation of the volume. So it's convenient to use the conservative form where you have a divergence here. So suppose I integrate this equation over the control volume, this green control volume. Okay. So differential equation is valid at each and every point inside the liquid region occupying the control volume. We'll integrate it and come up with an integral equation. Integral 4 terms. Here we have 2 terms on the left and 2 terms on the right. So you will have 2 integrals on the left and 2 integrals on the right. Okay. Now look at the middle integral. It is divergence. Okay. So you can use the Gauss divergence theorem and convert it to a surface integral. And then you can evaluate this fluxes by making assumptions regarding the velocity distribution. Okay. So the middle term, the volume integral on the second term on the left hand side, I can convert to a surface integral. And similarly, the last term here, del v del x, we have discussed this before. If one can use the divergence theorem, I left it as an exercise and write it as P and x dA. So if I take these two relations and substitute here, instead of having 4 volume integrals, you will have 2 volume integrals and 2 surface integrals. Okay. Now compare this result with what you might have obtained if you use Reynolds transport theorem, and you will see the result is the same, because the right hand side, the first term is the body force on the fluid, and the second term is the net surface force on the fluid. So sum of this integral on the right and this integral minus P and x dA will give you the net force acting on the fluid in this control volume, which is not including the solid vein. Okay. And the left hand side is exactly what you would get if you use Reynolds transport theorem in the translating frame. Okay. Now the good news is Gx prime is 0 and the flow is steady in the moving frame, translating frame. So first term will be 0 because del del t prime is 0. Note that del del t is not 0. Okay, but del del t prime is 0. So you will have just the flux of the momentum equal to the net force due to pressure. And again, this is of course not the pressure integrated over the surface of the vein, but over the surface of the control volume here. Okay, a closed surface. So because it's a closed surface, one can write this integral as replace P by the gauge pressure and the result will be the same because the atmospheric pressure will cancel out. The net effect of atmospheric pressure will cancel out. So P gauge multiplied by Nx, if we integrate over the surface of this green control volume, okay, you see that the gauge pressure is 0 at those parts of the control volume which is adjacent to the air. Okay, that is this point over here. Okay, and this surface. And we have seen it's a good approximation to say that inside the liquid the gauge pressure is 0 at section 1, section 2, and section 3. All right. So if I look at this integral, the left hand side, this integral I can write as the sum of two integrals. First one is the integral over the surface 4, and the other is an integral over the remaining surface. But on the remaining surface, the gauge pressure is 0, so this integral value will be 0. So simply what you'll get is that the net force due to pressure on the fluid inside this green control volume is the force due to the pressure on the surface 4. Okay. So this quantity here, which is minus of P Nx dA, I can simply write as minus of integral of the gauge pressure over this surface. Okay. So you have this simple relation that the integral of gauge pressure with the appropriate x component of the outward normal on the wetted surface of the bucket is minus of this flux. Okay, and this quantity we have seen is the force on the blade. So the force on the blade then is negative of the volume flux of the relative velocity, the x component. And this result is identical to what we had done last time using a different control volume which included the solid surface. So I hope that I have convinced you about two things. One is you need not always use a control volume which includes the solid surface. And the other thing is that there is an equivalence between the local equations and the global equations. One can integrate the local equation to get the global equation. Now, which is easier? Well, the other method was easier, so I did it first. The net result will be the same. Okay, here what you have to do is you have to look separately at the free body diagram of the solid. Okay, and the control volume, and then put them together. And in the other method, you are going to get the same result, but it's not rigorous. There are a lot of gaps. It's the connection between the two I have shown you, demonstrated through this example. Okay, now you might have recognized by now that this course is about energy conversion. Professor P.K. Das is talking about power plant engineering. There also you're trying to convert energy in the form of heat to useful work. And here in this part, we are trying to convert kinetic energy of fluid and potential energy of fluid and pressure of the fluid to work. So here you are converting the mechanical energy of the fluid to mechanical energy of the rotor, which will rotate the electric generator. So the mechanical energy of the rotating shaft will ultimately be converted to electrical energy. And in the other part, you will use the heat to boil water, and the steam might run the turbine. Okay. There also, you are going to pressurize the steam. So pressure of the steam will reduce, temperature will also reduce. So thermal effects coming. Okay. Now let us therefore see if we can get the prediction using the first law of thermodynamics. We have already got a number or prediction which is not exact, but anyway, you can't do better than this using such simple models. You have got a prediction using the linear momentum. And there, of course, we have assumed that the rotary motion can be approximated by a linear motion because the radius of the wheel is very large compared to the radius height of the bucket. Now let us use the first law. So you'll consider again a system which occupies a control volume and look at the energy of the system. So one way to look at it is consider the total energy to have the internal energy component, the kinetic energy, and the gravitational potential energy. Then the total energy of the system will be rho times the specific internal energy plus the specific kinetic energy plus the specific gravitational potential energy integrated over the volume. And this energy will increase if energy is transported in the form of heat to the boundaries of the control volume. And if there's an external force acting on the control volume boundaries, if the point of application of that force moves, there will be some external work which I'm calling W dot external. And because the fluid is moving, there will be some flow work. Now, here the first equation is in vector form. And FB, this external work, is the external force scalar product with the velocity of the blade. This is the rate at which work is done by the external force on the blade. And that is why I have a plus sign here. So when work is done on the blade, the energy will increase. And if you're interested in the power developed by the blade, it will be the minus of W dot external. Okay. And W dot external, if I say, is FB dot U, FB is minus the scalar FB times EX, and the vector U is the speed scalar U EX. Okay. Now EX dot EX is 1, so you have simply minus FBU. So the external force is minus FBU, and the power developed by the blade then will be the negative of this, which is plus FBU. Yeah.
What was E in the previous term?
What is
Like
E?
the energy balance. No. In the previous energy balance equation.
This is specific internal energy.
Okay. Yes, sir. Yes.
See, if you look at a book on thermodynamics, they'll probably use small u. Okay. Now, if you look at a book on fluid mechanics, quite often you'll see the symbol small u is used for the x component of velocity.
Yes, sir. Yes, sir. So they use E
So
for
to avoid
internal.
confusion,
Yes.
I have replaced the u by small e. So when you are looking at the first law, it is balance of total energy. So you have the heat interaction also. Okay. And you have the internal energy also. If you look at just the balance of mechanical energy, you will not have the E. Okay. You will not have the heat also. You will just have the work done. Okay. But if you have work done against viscous forces, the mechanical energy will reduce. We call it dissipation. But as you know, energy is neither created nor destroyed, so it is converted. So that conversion will increase the internal energy. So now I'm using the first law. Yeah. Any other questions?
No, sir.
Okay. Now So note what I want to emphasize is that when I look at this external work done by the external force, work will be done only if there's a displacement, and that will depend on your observation frame. Okay. So if you make the Galilean transformation and sit on the bucket which is translating, you'll see a force acting, but there is no displacement of the force. So observer in that frame will not see any work done. So if I replace this V by W, the relative velocity, okay, then this W external will be 0. Okay. So this is a subtle point. You need not worry about it. What I want to emphasize is that when calculating the W dot external, this velocity must be in a certain frame, and here I've used the ground frame or the stationary frame. And therefore, when looking at the kinetic energy, I'm using the fluid velocity in the same frame. Okay. So if I change my frame, then I have to change the definition of the kinetic energy. The problem, one of the problems is that if you look at just a book on thermodynamics, they'll not write the weight as a scalar product like this. Okay. But obviously there's a link. You can always use your mechanics concepts to relate the work done in thermodynamics to displacement of forces. Okay. So here the notation is W dot external is the work done by the force on the blade, and this will increase the energy of the fluid, so I have a plus sign here. Okay. And if I say that W dot is positive, if work is done by the system, then I will have a minus sign here. So later on I'll replace plus W dot external by this, what I'm calling minus PV. P for power now and B for blade. So right now we are looking at power developed by single blade. Later on we look at power developed by the entire turbine. Okay. Now we'll take a coordinate system which I've shown you before, and I was using Y for a vertical coordinate instead of Z. Okay. So G is minus GEY because Y is pointing upwards and G is downwards. So G dot R will be minus GEY dot the position vector. And EY dot EX is 0, EY dot EZ is 0, EY dot EY is 1. So this is minus GY. And this capital V is the fluid speed as measured in the stationary frame. So it's the absolute value of the vector V, fluid velocity, which is square root of V dot V. Okay. So when solving problems, we can start with this, which is coordinate invariant, but then convert it to the scalar. V dot V is V square, and minus G dot R is plus GY. So GY is the gravitational potential energy per unit mass, and half V squared is the kinetic energy per unit mass in the absolute frame. So this W dot is the work done as seen by an observer in the stationary frame. Now what is the flow work? Well, if you go back and look at this control volume, at this point, the fluid inside will exert a force on the fluid on the left, and the fluid on the left will exert an equal and opposite force on the fluid inside the control volume through this surface. And we are not looking at viscous effects, so it is just the flow due to force due to pressure. And this we'll say is approximately one-dimensional situation. So we are not looking at pressure variation across this boundary. It's a uniform pressure distribution. Okay. And there is work done if fluid is displaced. Now this green boundary is translating to the right, and the fluid is also moving. So the rate at which the fluid particle process is determined by the velocity relative to this surface, which we are calling W. Okay. So the work done at that interface, surface of the control volume, will be P1A1 times W1, the rate of work done. Okay. So this is Newton per meter square into meter square. So this quantity in parenthesis is the force. And per unit second, the movement of the fluid is W1 into the control volume. Now this is work done by the fluid outside the control volume on the fluid inside. The fluid is being pushed in. All right, since I've kept this term on the right hand side over here, I put a plus sign over here. Okay. Now similarly at section 2 and 3, the fluid is pushed out. Okay. So when the fluid is pushed out over here, the fluid inside is doing work on the fluid which is outside. So there will be a negative sign. One is work done on the fluid, other is work done by the fluid. So I've taken the convention that work done on the fluid is plus and work done by the fluid is minus. So if you look at the flow work, we'll have P2A2, W2. So just replace the subscript 1 by 2 here and 3 here. And there are minus signs here. Okay. Now A1 times W1 is the volume flow rate of fluid entering the translating control volume, which is a mass flow rate divided by rho. Rho is constant, it's a liquid. So here A1 I can write as M1 dot divided by rho. And A2 W2 I can write M2 dot divided by rho. And A3 W3 I can write as M3 dot divided by rho. So we have M1 dot into P1 by rho minus M2 dot P2 by rho minus M3 dot P3 by rho. Now P by rho, when the flow is steady and the density is constant, we have seen before, is like a potential energy associated with pressure. So this term is the change in that potential energy. And these are the mass flow rates. Mass flow rate into the control volume and the mass flow rate out of the control volume. Okay. Now let us go back over here to this equation. Instead of writing these three terms, let me introduce the symbol phi, which is the sum of the specific kinetic energy and this is specific gravitational potential energy. Okay. So what you have here is the net potential energy of the net total energy of the system. You can apply Reynolds transport theorem in the translating frame and write this as this temporal derivative plus the flux of this quantity phi through the control volume by the relative velocity here. And since the flow is steady, the first term is 0. Flow is steady in the translating frame. That's why I am using this form. So this now, if you look at this flux, there's an inlet and there are two outlets. So it will be rho phi at the inlet into minus of W1A1, which is W dot N dA in a one-dimensional situation. So W dot N is negative in the inlet and W dot N is positive at the outlet. Okay. So rho times W times area is the mass flow rate. So you see that the flux of the property is minus M1 dot phi 1 plus M2 dot phi 2 plus M3 dot phi 3. So phi 1, phi 2, phi 3 are the values of phi at 1, 2 and 3. So at the inlet, so this is the net efflux. So from the inlet you have a negative sign because it is coming in. Okay, W dot N is negative. And from the outlet it is positive. So net efflux is outflux minus influx. So this is the influx and this is the outflux and this is the net efflux. So if I take this and go back and substitute over here, the first term is 0 and second term I can write simply as an algebraic equation. And then on the right hand side you have the heat term, the external force and the flow work. It is a simple matter of substituting and you will come up with the steady flow energy equation. So you have minus M1 dot phi 1 plus M2 dot phi 2 plus M3 dot phi 3. So this is the net flux of energy, efflux of energy through the control surface. The right hand side is the addition of energy due to the heat, subtraction of energy due to extraction of work by the turbine. So earlier I had plus W dot external, now I'm writing minus PV and plus the flow work done. Okay. Now we are interested in the power developed by the blade. So move this PV to the left hand side and move the other terms to the right hand side. And you will see that you have the reduction in the pressure potential energy plus the reduction in the total energy of the fluid flowing through the control volume plus the heat which is added in. Okay, and this phi of course stands for sum of three quantities. So I can write this as sum of a group of terms involving internal energy, a group of terms involving kinetic energy, and a group of terms involving potential energy. So you have four terms on the right hand side. One is involving the pressure change, one involves the change in internal energy, one involves the change in kinetic energy, one involves the change in gravitational potential energy, and the other involves the heat which is being added. Okay, so we are almost running out of time. We'll continue tomorrow, but what I want to show you is the source of the power. Okay, in general, we will have similar equations for other turbines. The power that you're extracting from the fluid may come from a reduction in pressure, a reduction in kinetic energy, and a reduction in potential energy. And in this part of the course, we are going to neglect the change in internal energy and the heat added. Those will be grouped together as the head loss term. Okay. And in the other part of the course, we are going to have Q dot in also, at least as far as the boiler is concerned and the condenser is concerned. But as far as the steam turbine itself is concerned, it will be adiabatic. So this will be zero. But you may have a change in the internal energy also. Any questions? All right. So we'll meet again tomorrow at 4 p.m.